So this is page 4 of the fault tolerance notes, and continuing on with the clock properties. When you are creating an application and depending on a clock, you make assumptions about how the clock's going to behave, like it's not going to run backwards and stuff like that. So violating those assumptions or those properties on the previous page could result in unexpected behavior from the application. So let's just look at an example where we have a 32,768 Hertz clock is 100 milliseconds fast, and we want to correct it. So a sudden correction, e.g. subtract 100 milliseconds from its current time, would do this. So it would satisfy property 1, having the correct time. Property 2 about the bounded drift, well, the clock has the drift, so it's not going to really do anything about that. But it would violate property 3, because if the application read the clock just before the correction and then read it after the correction, it could see time running backwards. And it might also violate property 4 if one of the intervals that your application is measuring happens to be across when that correction takes place. So as a result of this, a gradual correction is preferred. So basically slow the clock down. And one way that we can do that quite gradually is to just, instead of counting 32,768 ticks as 1 second, we'll count one more than that as 1 second. So count 32,768 plus 1 ticks as 1 second. And this would slow the clock by 1 over 32,768 hertz. Remember, hertz is 1 over seconds, and so rounding, that gives you 3.05 times 10 to the negative 5 seconds. So then the question is, if you're slowing it by that much, how long is it going to take for that correction to get you back to the correct time? So the correction will take 0.1, that's 100 milliseconds, over 3.05 times 10 to the negative 5 seconds equals 3,276.9 seconds, which is approximately 55 minutes. And you get to work with this. So see problem set 7, and it's question 1. We'll elaborate on this.